it is indeed required to pull a ground wire to feed direct current panels. The primary reason for this requirement is safety. The ground wire serves as a critical component in providing a low impedance path for fault currents to return to the source. This low impedance path is essential for ensuring that overcurrent protection devices, such as circuit breakers or fuses, operate correctly and promptly in the event of a fault. Without a ground wire, fault currents may find alternative, unintended paths to flow back to the source. These alternative paths often have higher impedance, which limits the magnitude of the fault current. This, in turn, can prevent the overcurrent protection devices from tripping or blowing as quickly as they should. As a result, the fault can persist for a longer duration, increasing the risk of electrical shock, fire, and equipment damage. Moreover, the unintended paths that fault currents take in the absence of ground wire can involve conductive materials or equipment that are not designed to carry such currents. This can lead to overheating, insulation breakdown, and even arcing faults, which are particularly dangerous and can easily ignite nearby combustible materials. Grounding, on the other hand, provides a dedicated, low-resistance pathway for fault currents, ensuring that they are quickly and safely directed back to the source. This allows the overcurrent protection devices to clear the fault rapidly, minimizing the risk of harm to people and property. Now let's talk about the ground wire. In direct current branch circuits, it is required to pull a ground wire to feed direct current branch circuits. The reasoning is exactly the same as for direct current panels. The ground wire provides a low impedance path for fault currents to return to the source, ensuring safety and proper operation of overcurrent protection devices. Just as with direct current panels, the absence of a ground wire in direct current branch circuits can lead to fault currents flowing through unintended paths, creating a safety hazard and potentially damaging equipment. The low impedance path provided by the ground wire allows for rapid clearing of faults, reducing the risk of electrical shock, fire, and equipment damage. The National Electrical Code, commonly referred to as the NEC, sets forth the standards for safe electrical installations in the United States. The NEC addresses grounding requirements for both direct current panels and branch circuits to minimize electrical hazards and ensure the safety of people and property. Grounding requirements are found in Article 690.8 and 690.31. Article 690 pertains specifically to solar photovoltaic systems, which often involve direct current power. Within Article 690, Section 690.8 may address overcurrent protection for direct current circuits. This may include specifications for conductor ampacity, overcurrent device ratings, and the coordination of overcurrent protection devices to ensure that they operate correctly in the event of a fault. Section 690.31 outlines the wiring methods and materials that are permitted for direct current circuits in solar photovoltaic systems. This section may specify the types of conductors that can be used, the methods for installing and supporting conductors, and the requirements for protecting conductors from physical damage and environmental factors. Now let's consider additional relevant NEC sections. Article 250 of the NEC is dedicated to grounding and bonding. This article provides comprehensive requirements for grounding electrical systems, including direct current systems. It covers topics such as the purpose of grounding, the types of grounding systems, the methods for grounding electrodes, and the requirements for bonding metal parts to ensure electrical continuity. There are various types of grounding systems, each with its own characteristics and applications. The NEC recognizes several types of grounding systems, including the grounded system, the ungrounded system, and the impedance grounded system. In a grounded system, one of the circuit conductors is intentionally connected to earth, providing a reference point for voltage and facilitating the operation of overcurrent protection devices. In an ungrounded system, none of the circuit conductors are intentionally connected to earth, which can provide increased protection against ground faults but may also make it more difficult to detect ground faults. An impedance grounded system uses an impedance, such as a resistor, to limit the current that can flow to ground in the event of a fault. Grounding electrodes are used to connect the grounding system to the earth. The NEC specifies the types of grounding electrodes that are permitted, such as ground rods, ground plates, and metal underground water pipes. It also specifies the requirements for installing and maintaining grounding electrodes to ensure that they provide a low resistance connection to earth. Bonding involves connecting metal parts of the electrical system together to ensure electrical continuity. This helps to create a low impedance path for fault currents, allowing overcurrent protection devices to operate correctly. The NEC specifies the requirements for bonding metal parts such as metal conduits, metal enclosures, and equipment grounding conductors. Equipment grounding conductors, often referred to as EGC, are used to connect the metal parts of equipment to the grounding system. This provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to operate correctly. The NEC specifies the requirements for equipment grounding conductors, including their size, material, and installation methods. Ground fault circuit interrupters, known as GFCIs, are devices that are designed to protect people from electrical shock. They work by monitoring the current flowing in the circuit and tripping if they detect a difference between the current flowing to the load and the current returning from the load. This difference indicates that current is leaking to ground, which could pose a shock hazard. The NEC requires GFCIs in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electrical shock. Arc fault circuit interrupters, or SIs, are devices that are designed to protect against fires caused by arcing faults. Arcing faults occur when electricity jumps between conductors or between a conductor and ground. These faults can generate high temperatures that can ignite nearby combustible materials. The NEC requires SIs in certain locations, such as bedrooms, to provide increased protection against fires. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other events that introduce high voltage transients into the electrical system. SPD work by diverting the surge current to ground, protecting the equipment from damage. The NEC recommends the use of SPD in certain applications to protect sensitive electronic equipment. Now let's discuss some practical considerations for grounding direct current systems. When designing and installing direct current systems, it is important to follow the NEC requirements for grounding and bonding. This includes selecting the appropriate grounding system, installing grounding electrodes correctly, and ensuring that all metal parts are properly bonded together. It is also important to use the correct size and type of equipment grounding conductors to provide a low impedance path for fault currents. Regular inspection and maintenance of the grounding system are essential to ensure that it is functioning properly. This includes checking the grounding electrodes for corrosion, verifying the continuity of bonding connections, and testing the operation of GFCIs and SIs. Any deficiencies should be corrected promptly to maintain the safety and reliability of the electrical system. Here are some of the common grounding mistakes to avoid. Neglecting to ground direct current panels or branch circuits is a serious safety hazard. Always ensure that all direct current systems are properly grounded in accordance with the NEC. Using undersized equipment grounding conductors can limit the effectiveness of the grounding system. Always use the correct size equipment grounding conductors as specified in the NEC. Improperly installed grounding electrodes can result in a high resistance connection to earth. Always follow the NEC requirements for installing grounding electrodes to ensure a low resistance connection. Failing to bond metal parts together can create a high impedance path for fault currents. Always ensure that all metal parts are properly bonded together to provide a low impedance path. Ignoring the NEC requirements for grounding and bonding can lead to unsafe electrical installations. Always follow the NEC requirements to ensure the safety and reliability of the electrical system. In conclusion, it is mandatory to pull a ground wire to feed both direct current panels and branch circuits in accordance with the National Electrical Code. Neglecting to do so can compromise safety and increase the risk of electrical hazards. By following the NEC requirements for grounding and bonding, you can ensure the safety and reliability of direct current electrical systems. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about grounding direct current systems. Electrical safety is paramount, and it is essential to take all necessary precautions to protect people and property from electrical hazards.